let us practice the unsymmetrical fall for this particular problem. Okay, this is problem 12.14 from Arthur and Bergen. Okay, Bergen, Whittle. Okay, this is from Arthur Bergen and V.Vittal. Okay, and V.Vittal. All right. The power system is given as below. Okay, we have a three-bus power system, and we have generators, two generators connected to bus one and bus two, and the connection is wired transformer. The generator one is on the bus one side, right, and it is solidly grounded on both primary and secondary, while the G2 it's delta connection on primary side. Okay, the solidly wide or solid ground wide is on the secondary sides of the generator G2, right? And the problem, I mean, the parameters are given like this. So we have the generator parameter of positive and negative. These are positive reactance and the negative reactance. So you remember from the lecture that the positive and negative parameters can be assumed to be identical, right? This is for simplicity. All right. If you have different parameters, so you have to analyze separately, right? You remember from the lecture that when we have to analyze it in unbalanced operation or unsymmetrical fault, this is about unsymmetrical fault, right? You remember that when we analyze it, we have sequence networks, right? We have a sequence network, and the property of which we have a positive and negative sequence. Okay, and you could write it in terms of one or two. One would be positive sequence, and two would represents the negative sequence. Okay, so these two sequences are have the same topology, but the difference is only in which the positive sequence has a voltage source connected to it, while the topology of the second, I mean, for the negative sequence would be identical to the positive sequence, but there is no source connected to it. Okay, so obviously, right, the sequence parameters, positive, negative sequence parameters are given, right? We have positive sequence and we have zero sequence parameters. So for the generator, it's given like this one. Okay, the generator 0.2 and 0.05 for zero sequence. And the transformer doesn't have any positive or negative sequence, different parameters, right? So the parameters for all the sequence network are identical. So the transformer would represent by 0.05 pu, and the line parameter positive and zero sequence are given, right? So the problem says that the pre-fault voltage can be assumed at VAN and VAG. PF would stands for pre-fault condition. This is pre-fault condition, right? So the pre-fault condition at bus 3 is the angle of 0 per unit, okay? And if we assume that the disturbance or the fault type is a single line to ground, in this case because the short circuit is at phase A with respect to ground, so it short circuit from A to ground. So this is single line to ground fault at bus 3. So the problem asks you to determine the IAF, IBF, ICF, the voltage. I mean the current at during the fault for phase A, B, C, right? And the voltage during the fault. VA, VAG, VA with respect to ground, VB with respect to ground, and VC with respect to the ground at bus 3. So you can see from the diagram itself that we assume that the fault happens at but 3, right? But it is just only at phase A. So this is single line to ground. So this is SLG. Okay, this is simple, right? I would suggest that before you go to see the solution, okay, why don't you just pause the video and we will come back later for the solution. Okay, let's take your time. All right. I hope you have done this one. Okay, you have done the solution. Okay, I will try to explain this to you. This is the very interesting problem, right? So the way that we're gonna solve this problem, we have to write the positive, negative, and zero sequence. Okay, and we remember single line to ground for the connection or interconnection of the three sequence network is in series, right? I will redraw this for you. Okay, this is positive sequence where you have the positive, I mean the both the source with the 1 point at the angle of 0 pu. This is a pre-fault voltage. Okay, and this is the C1. Okay, and we have C2. Okay, this can be C2, and this is C0, negative zero sequence, right? And these are connected in this way, okay? And this is the what we can say that this is like a load of this sequence network, which is in this case it is the 3 times of CF, okay? But in this case, since we assume that it is solidly grounded, okay, did we what is specified somewhere? I mean, do we have any specification somewhere? No. If not specified somewhere, right? We can say that this is the solidary ground. Okay. I mean, this is it's specified from the picture itself because the picture from the ground there is no impedance between the ground. So the C, I mean the CN short circuit impedance is 0. So this is 0. All right. So what you have to do here is that you need to determine the C1, C2, and C0. This is the Thevenin's equivalence for each of the phase sequence. I mean the sequence networks, right? And we have to plan, and then you just plug into the equation, right? What you have to see, what you want to see is that from this case, this is I1, and this is I2, and this is I3. Okay, I1 and I2 and I3s are identical in this case. So I1 is equal to I2 is equal to I0, which is 1, the angle of 0 divided by C1 plus C2 plus C0. Okay, the sum of all the um, impedances, right? So in this case, the first step is that we need to determine, right? For the first step is that we need to determine, okay, the Thevenin equivalent for zero, positive, and negative sequence networks. Okay, so let us start by analyzing the positive and negative sequence. For this case, you see that the given parameters, right? The given parameters, you can see that the positive and negative sequence parameters are all identical. So that means that when you write the equivalent circuit, right? Just do it once, okay? If you do the positive positive network, okay, you don't need to redo. You don't need to recalculate the Thevenins for the negative sequence network because the parameters are identical, right? So let us draw this equivalence network. Okay, this has been done quite a few times already, right? you can see that in this case, right, when we write the positive, okay, positive sequence, you have to have the voltage source, right? But later on, when you try to find the Thevenin equivalence, I mean the Thevenin impedance, okay, what we have to do is that we have to we have to deactivate the source, okay? So for simplicity, okay, I don't want to, draw everything and delete the voltage source. But what you have to know is that, when we want to find the Thevenin's equivalence, right, you have to deactivate the source. So I don't need to draw the voltage source in this case, okay. So the voltage source is represented as a short circuit, right? And you have the generator G1, the G1 in this case, and the parameters are given, right? Was given by point 2. I'm not mistaken, this is point 2. So this is J point 2, and it's connected through the transformer. So in this case, the connection of the three-phase transformer does matter, okay, when you consider just positive sequence. Zero sequence. Okay, you remember that the delta connection in this case for the three-phase transformer will play the role just in the zero sequence network. Okay, so you have to take a precaution to that zero sequence. You remember that when we have the delta, the short circuit current will not flow through over a delta. So we normally represent the delta path, the side that we have delta by opening the delta from the ground, so that there is no current flowing from in this path. Okay, we just remove the connection between that point to the ground. This is all what we have to do. Okay, but this is what we are analyzing is positive. Okay, and in this case, this is the same as the negative sequence network. Okay, because the parameters are the same. Okay, and we have the transformer, right? The transformer it's 0.05. Okay, now we arrive at the bus one. The bus one would look like this. We have the bus 3 to the connection between 1 to 2. Okay, this is 2, and the parameter of the transmission line is the J.01 to 0.1. Okay, and from here you have from 2 you have another transformer is J.05, and in this case, okay, we are at this point, so we connect this point to the reactance, subtransition reactance of the generator G2, which is 0.2. Okay, so now we are at the internal EMF, but in this case we are interested in just the Thevenin's equivalence impedance, right? So we just deactivate the source. What you can see here is that we are still having one bus 3 left. Okay, so the 3 just connect between what? Between 1 and 2, right? So if I put the node 3 here, okay, and there are 2 transmission lines, right, connected between 1 and 3, okay, and 3 and 2, okay. This is it's like this one, okay. Okay, and in this case we have all the parameters are the same. This is 0.1 for these two, okay, for these two from 1 to 3 and from 2 to 3. Okay, and what you need to do here, this is the complete picture, right? And then what you need to do for trying to find the equivalence, Thevenin equivalence from at bus 3, right? Because the fault happens at bus 3, so you need to find the C Thevenin when you look from bus 3. Okay, looking from bus 3. You have to find the Thevenin when you're looking from bus 3. Okay, how we can do it? Okay, the idea is that we want to find the equivalence impedance. So we want to when you stand here, when you stand over here, you're trying to look into bus 3 with respect to ground, right? How much do you see this, the whole bunch of this impedance? Okay, so the idea is pretty simple. I think it's just like what when we analyze in the transient stability, right? You still remember we have this connection of between bus 1 to 3 as a delta, right? In this case, it would be much easier, right? And you transform this the delta connection at this bunch, okay, at this group, okay. If you transform this into delta, okay, what you can do is that you have the delta, and this is your neutral, and this is delta, and this is delta, okay. When you have the delta, you can see that when you want to find when you stand from this point at bus 3 with respect to ground, okay, you have the parallel connection between, okay, the neutral all the way from these two routes, okay. If I want to show you this, okay, this from neutral point, and when if for example, if what you can do is that if you want to see to find the Thevenin's equivalence from the circuit theory, right? What you have to do is like this. You have the CTH here. You deactivate the source, which is what we have done it already. You deactivate these two sources. Okay, you want to see the CTH like this. So you, for example, here, if you put the current, right, for the test current 1 amp, okay, and the current 1 amp will go through this port, okay. This is bus 3, for example. If you stand at this bus 3, okay, and this would create the polarity, I mean the current flowing through that impedance, so that would create the voltage drop across this point. It's equal to CTH, okay. And if you measure the voltage with respect to the ground, in this case you measure the voltage like this is V measure, okay. Now you can see that all right, the V measure in this case, the V mesh, okay, the the voltage measure that you find here is essentially CTH, all right. That's what that's what we have learned from the circuit theory. So it's just the same, okay. If you put the current flowing into bus 3 in this case, all right, you can see that if you have already transformed, this into this picture, okay. Let me delete this picture a little bit. So this is bad, okay. It's all destroyed. Let me rewrite this one. If you have, this is bus 3 and 3 to 2, okay. Yeah, you have, if you transform this, the transformation is simple, right? The y transformation, you remember, this is when you transform this to this, delta to y, right? The impedance will be reduced by 1/3, okay. So the impedance in each branch of this is j.1 divided by 3. This is j.1 divided by 3. It's all equal, okay. Now you can see that if you put the current, the test current 1 amp to here, so the test current will flow like this. This is 1 amp, and the 1 amp here, when it comes to the neutral point here, it will have the two routes to flow, okay, the two routes to flow. So that means that the route down below, okay, if you see from this, the route this is the first route that the current will flow, okay, and this is the division of the current on the to the other side as well. The current can flow in this direction as well, okay. And the sum of these two color, I mean the purple and the green, right? The sum of these two will be 1 amps. So you can see that the Thevenin equivalence for this is what? So that's what is C TH for this case is a C equivalence of positive, right? That is just the same as the CEQ of the negative sequence because the parameters are equal, right? The parameters are equal. So you can see that it can be determined from the, okay, when you go this, it will go through J point zero 0.01, point 1 over divided by 3 plus the parallel between these two roots. Okay, the parallel between the green roots and the purple roots. All right, so you can see that the green one and the purple one has the same, okay, equivalence impedance because the three elements on the green roots are all the same as the three elements on the right roots. Okay, so you have two identical impedances in parallel, right? So that means that this is just a half of the sum of these three elements. Okay, because you see we have point 1 point 1 divided by 3 plus 0.25, right? So these two routes are having the same thing. So once you put this into parallel, so this is just half of the total impedances. So this is point 2 plus 0.05 plus 0.1 divided by 3. So all these are equal. I mean, this is the equivalence impedance. In this case, I will leave this for your own calculations, and this is if you hit the calculator, this should be 1.175 pu. All right, 1.175 pu. Okay. Now, I think it's pretty simple, right? So the idea is that at this connection of the transmission line, okay, this is the delta connection of this transmission line. We would represent this as the star, right? So for the for the zero sequence, right? I will draw this the delta connection first. Okay. Okay, this is the delta connection. This is bus 3, and this is bus 1, this is bus 2, and this is, of course, this is neutral. Okay, so the parameter given here in this case, the zero sequence of the transmission line, the zero sequence of the transmission line is given as a 0.3. This is simple, right? 0.3, this is 0.3. You can see that if this is 0.3, then each of this branch is 0.1. Okay, the 0.1. And here for this side, you have the transformer, you have the generator. Okay, so the transformer is in this case the parameter is 0.5. Okay, it remains unchanged from the positive sequence, and in this case the zero sequence of the generator is 0.5 as well. So we can draw in this way, right? The from bus 2, okay, from bus 2, what you can see is that from bus 2, the parameters of the transformer is on this side. So the transformer is on this side of the primary side. We can see that this is 0.05 in this case, and in this case, it is an open, it's a delta, right? It's a delta on this side. So zero sequence, you don't have the voltage source, and this is it connected to the ground in this case. Okay, this is open due to the delta on this side. All right. Similarly, you want to find the Thevenin's equivalence from bus 3 with respect to ground. Okay, so if you put the current into this network, right, it's 1 amp here. Okay, the 1 amp when it goes to the ground, to the neutral, right, there are two paths. This is the first path. This is the first path is on this side of the line. This is the first path. Okay, and that will go from the second path will go this like this. Okay, so you can see that this is a closed circuit. Okay, now you can see that the CEQ of the zero sequence would be J.1 plus, okay, the parallel of these two routes, these two, okay. So you have the parallel between J, the parallel between point 2 in parallel with point, is it right? Point 2 and point 1.5, right? Point 2 and point 1.5. So in this case, you have 0.2 and 0.15. Now you can calculate this one yourself. Okay, this has been between the multiplication divided by the sum. So finally, you have 0.01857 pu. Okay, this is the CEQ the Thevenin equivalence of the zero sequence. Okay. As I said earlier, right, we have to determine the sequence current. In this case, the sequence current for all the networks, zero, positive, and negative sequence are all equal, right? In this case, we just take the value that you computed from earlier, right? The compute that the C1, C2, and Z0 computed earlier, and you put in this equation. So you have 1 an angle of 0 plus j times, in this case, you have 1 and 2 are the same. I mean, C1, C2 are the same. You have 0.175 multiplied by 2 because these C1 and C2s are the same, plus j of C0, which is 0.1857, right? So in this case, you have negative j of 1.8667 pu, right? This is what you have seen. Okay, you can determine from I0, I2, I1, right? This is our I0, 1, 2. Okay, now you can use the transformation, all right, but from the transformation you can see that when we transform this, you need to multiply, you know, this is I0, I1, I2, and on the other side you have IA, IB, and IC, right? Now in this case it's simple. Okay, you don't need to determine the IB and IC because the short circuit just happened at phase A only. So you can answer straight away that IB and IC here must be 0. Okay, it must be 0. You don't need to calculate anything. Okay, and the question also asks you, okay, IAF, IBF, and ICF. So without having any need to compute, right? IBF, ICF, you can answer straight away that it is 0 per unit. It must be 0 because it is or 0 per unit or 0 amp. That it doesn't matter, right? It must be 0. Okay, it has to be 0. So the IA is what? It is an IA. So you remember the first row of this matrix. Okay, it is it's all 1. Okay, this is the transformation, right? This is A. Okay, this is a matrix A, the first row of the matrix A. So the IA itself is what? Is I0 plus I1 plus I2, or it is 3 times higher than this guy. Okay, this is the 3 times higher than it can be I1. Okay, because I0, 1, 2, 3 are the same, so it is 3 times of this guy, negative j of 1.8667. So you have negative of j 5.6001 pu. Okay, this is IA. Okay, and this is the answer. Okay, this is the current or the short circuit current, right? Now, the problem also asks you to compute the voltage, right? It's not that difficult, okay? You need to just remember this, okay? Because you want to find the VA, VB, and VC. So VA, VB, VC it can be computed from the A matrix multiplied with the V0, V1, V2. This is the voltage in the phase quantity. I mean in the sequence quantities. This is the matrix 1, 1, 1, 1, A square times, and this is A square, right? And remember A is 1 and the angle of 120 degree. So what you have to do is that, you have to start from calculating this V0, V1, V2, right? And you plug into this equation and you find the VA, VB, VC. And this is the answer, right? This side is the answer for this question, okay? And first thing is that you need to, what are our V0, V1, V2? Okay, you just go back to the equivalent circuit, right? So the V1 is here. This is a positive sequence, right? And the pre-fall voltage is 1, the angle of 0, and the C1 was, how much was it? J.175, and this is V1, okay? And this is V1. So your V1 here would be the 1 angle of 0 minus, this is an I, this is I1, right? This is I1, and this is a voltage drop, okay? You have to, the voltage at the source minus the voltage drop at this impedance, so you have V1, okay? And V1 is 1 angle of 0, and you subtract this by, I1. What was I1? Your I1 was negative J 1.8667 times by the J 0.175. All right. Okay. Now in this case, you can see that the voltage has to be less in this case because J times J is negative 1, okay, plus I mean negative times negative become plus. So you have 1, okay, 1 and minus, right? 1 minus multiplication of 1.6 multiplied by 75, right? So you end up having, the voltage of V1 at the 0.6733 pu. You see, this is in real quantity, right? This is V1. For V2, okay, V2 and V0, V2 and V0, you don't have a voltage source, okay? This is easy. For example, this is C2, okay, and you want to find V2. In this case, this is I2, right? So you can see that the current I2 flowing through the impedance C2, that would create the polarity plus at this side and minus at this side. Now you can see that the two polarity, I mean the two signs are just opposing to each other. So your V2 has to be negative of this, okay, negative of I2 times C2, okay, it becomes negative of I2. I2 was this guy, negative J 1.8667 times J 0.175, right? The C2 is the same as C1, right? Now you can see that this is what? J times J is negative, right? And this is positive. These two multiplication are positive. So this has become negative. What is a negative? Negative of 0.3267 pu. So similarly, okay, the V0, right? The V0 here is what? V0, you have to get the negative of, right? Negative of negative j 1.8667 multiplied by j times 0.1857. This is the C0, right? Okay, so you get minus 0.3466 pu. Okay, then having these three figures, right? You have these three figures, this one, this, and this. You put these three numbers into the right side of this equation. Okay, you put these three figures into the right side of this equation. So you can identify. You can oh, you can find V1, V2. Now you plug in this figure into this side, so the final value would be 0. In this case, 1.01, angle of negative 120, 0.98 degree. The same 1.01, but a different angle, 120. 0.98 degree. This is in PU. Okay, that's all for this example, right? We will try another problem. Okay. Okay. See you in the next clip.